I'm going to talk about waves. All right? Some examples of waves: water waves, such as are caused when you drop a rock in a lake. Rope waves, such as when you vibrate one end of a rope. Sound waves, such as are created from my voice right now as I'm speaking. Light waves, such as when you turn on a flashlight. Radio waves, such as from a radio station. And even human waves. Okay, think about if you've ever been to a stadium event and everybody gets up out of their chair and throws up their hands in the air in a coordinated fashion so that a wave moves around the stadium. Okay? Now, there is something a little bit odd about waves that you may not have noticed. So, no matter actually moves. Okay? Waves are not an object composed of matter. Okay? Think about the human wave. Okay? There's nobody running around the stadium along with the wave, is there? In fact, isn't everybody moving vertically? All right? Yet the wave is moving horizontally, right? So a wave is, what is a wave, you might ask? Okay? So let me type out what waves are so that there's no misunderstanding. Waves are disturbances that travel through a medium. All right, so a rope wave is traveling through the rope. Water waves travel through water. Sound waves travel through air. All right, so there's always a medium, and there's some kind of disturbance traveling through the medium. All right, waves can transport energy, but not matter. All right, if matter was being transported, it would be something else besides a wave. Okay, and so as I've already stated, some examples, right? Rope waves, water waves, human waves, sound waves, light waves. Okay. Now, what I'd like to do is give you some parameters to describe waves. So, as an example, let's think about the rope wave. So, we're vibrating a rope and it's causing a wave to move down a rope. Now, let me make an XY coordinate plane. And let's say that the rope is the rope was initially resting on the x-axis, and somebody started vibrating the rope so that the bits of the rope are moving up and down in the y direction. Okay? So if somebody was vibrating the wave in the same manner over and over again, the shape of the wave would mimic a periodic function. Okay, so it could be lots of different periodic functions, but let me just draw a sine wave for an example. Okay, now again, the type of periodic function is not so important right now. We understand that waves can be lots of different shapes. Okay? What I want to focus on now is not the shape of the wave, but rather some other properties of it. So there will be a pattern, a portion that you can reproduce the entire wave with by simply placing copies right next to each other. All right. So, for example, my blue curve is several copies of this little mountain-shaped piece. Okay, if you placed several copies right next to each other, you would reproduce the entire blue curve. Okay, now the length of that piece that you are copying over again, okay, that is called the wavelength. And it's traditionally denoted by the Greek letter lambda. Okay? Now, the pieces for this type of wave are moving away from the position they had before the vibrations, the pieces of the rope. Okay? So the deviations from this center line, okay, that is referred to as the amplitude. Okay, so a capital letter A is a common name for that parameter. All right, now the next one I can't really, is not a length like wavelength and amplitude. So wavelength and amplitude you can specify those in units of meters. Okay, the next one is with respect to time. So every piece of the rope, let me put a red dot on some piece of the rope. Okay, so the piece of the rope that I've just marked in red, along with all the other pieces of the rope, are moving up and down. Okay, now the amount of time that it takes any piece to complete a full cycle, in this case all the way down and all the way up, that is referred to as the period. Okay, and a common name for the period is T, capital T. All right, and then we have one more variable to introduce. So in addition to talking about the period, which is the length and time of a cycle, we can ask ourselves, how many cycles do we have per unit time? Okay, that's referred to as the frequency. And that's typically denoted by the letter F, and that's equal to the inverse of the period. Okay, F is equal to 1 over T. Now, the disturbance will be, for this example, will be moving to the right. Okay, it'll have a certain rate of change of position. Okay, so let me draw an arrow to signify that motion of the disturbance. Okay, and that is referred to, of course, as the velocity, denoted by the letter V. Okay? Now, there is a relation between the wavelength and the period, which you might catch if you think about this carefully for a few moments. So, how long do you think it takes the disturbance to move one wavelength to the right? Okay? Can you see that that has to be coordinated with the period? In other words, how long it takes any piece to move in one cycle, all the way down and all the way up? Okay? Can you maybe see that for the disturbance to move a wavelength, every piece has to move one cycle? So what I'm trying to say is that the velocity will always be the disturbance will always move one wavelength in one period. Okay, so that will turn out to be a very handy formula. The velocity is equal to the wavelength over the period, or equivalently, the velocity is the wavelength times the frequency. Okay? And that's because, again, the frequency is the inverse of the period. All right? So, very important formulas to remember. Now, let me repeat that these formulas, these parameters, are not just for sine-shaped waves. Okay? Here is another possible shape for a rope wave. Give me a minute to make a picture. Okay, I've drawn a picture of what's referred to as a square wave. Okay, so even though it's not a sine-shaped wave, we can still define an amplitude, a period, frequency, wavelength. Okay, in fact, can you see that for this example, the wavelength is 4 centimeters? Okay, the amplitude is 6 centimeters. All right, and the disturbance will be moving at some rate to the left or right. Okay, so we can clearly define a velocity. Okay, and every piece of the rope is going to be moving down and up, so we can measure that time, so we can define a period, and then the frequency is the inverse of that. Okay, so again, these parameters are for all types of waves. Now let me have you do an exercise. I'm going to draw a picture of a rope wave, and I want you to determine some parameters of the wave. So give me a minute to make a picture. Okay, so I've drawn what's referred to as a square wave, and let's say that the period of the square wave is 4 seconds. Okay, the lengths are given in units of feet, so what I'd like you to determine is the amplitude, the wavelength, the frequency, and the velocity. Okay, do as much of that as you can. Pause the video if you have to. Okay, so do that now, please. Okay, so I will go ahead and work it out also, So the amplitude is 50 feet. The wavelength, you could measure 2 points that correspond to each other. So, for example, I have here the x-intercept as the rope wave is as the rope is going up through the x-axis, and then so the corresponding point would be over here. That's another point where the rope is going up through the x-axis. The distance between those two red dots is 10 feet. All right. The frequency is the inverse of the period, so 1/4. And the units for frequency, cycles per second, okay, also referred to as hertz. And velocity. So I didn't tell you how fast the wave, the disturbance was moving to the right. However, we know that the velocity is equal to the wavelength divided by the period, right? So that's 10 divided by 4, right? Or 5/2, or 2.5 feet per second. All right, now let me have you do a few more exercises. Suppose that I had a wave with a wavelength of 2 meters and a velocity of 10 meters per second. Could you tell me what the period of that wave is? So pause the video if you have to and work this out now if you like. All right, so I'll go ahead and do it. So the velocity is the wavelength divided by the period. So Vt equals lambda from cross multiplication. So the period is lambda divided by velocity, or 2 divided by 10, or 0.2 seconds. All right? Now let's do one more. Suppose this time you knew the frequency of a wave, 6 hertz or 6 cycles per second, and the wavelength, 4 centimeters. All right. Now, could you tell me what the velocity of this wave is in meters per second? So pause the video and do that now, please. Okay, so I'll go ahead and work this out. So the velocity is lambda times the frequency, so 0.04 times 6, and that is 0.24 meters per second, using the velocity formula that I gave you earlier.